Hi, in today's tutorial we are going to learn how to classify 100 different classes of sports images. So, this tutorial is part of this playlist that contains several classification tutorials. You are most welcome to subscribe my channels. More tutorials will be uploaded soon. So let's jump into the demo and it will be more clear. So let's run a short demo and explain what we are going to do today. We'll start with take this 100 sports image classification. As you can see here, it's contained more than 13,000 of terrain images that are all divided and categorized to 100 images. This is, for example, air hockey, and this is, for example, basketball. These are basketball images. So there are many images here in 100 categories. So basically we will learn how to create a content environment with all the relevant Python libraries. We will learn to use the EfficientNet model or architecture and learn how to customize it to our own needs, and we'll learn to evaluate the results, and after that we will run an inference process for one of the test images. For example, this is a bike polo, but of course you can choose any other sports images out of the 100 category. So 100 categories, it's a lot, and basically running for 13,000 images, it's a process that took about 1 hour. But we have a great model that works fine with the results. Here is our test image. As you can see, this is a bike polo. This is the original dimension of the image. All the images are on 224 by 224, so they are ready for training. Let's start with the installation part. I'm using a TensorFlow, and in order to utilize the GPU card, I'm running on Linux. So basically it's a WSL2 environment that was installed in Windows to generate a Linux environment. So as I mentioned, this is under PowerShell, and the WSL running under the PowerShell. So first of all, let's create a new conda environment. I name it TensorFlow 217. Of course, you can choose your own custom name, and it's based on Python 3.12. Then of course we should activate the environment in order to install the next Python libraries. And next we need to install the TensorFlow. You can also run it on a Windows machine. So if you run it on Windows machine, you run this command. This will install TensorFlow that utilized only the CPU. And if you would like to run the GPU, you have to run this command that includes the end CUDA. There is more documentation in this link. So after you install the TensorFlow, you have to install several more Python libraries like Matplotlib, datasets, Pillow, and OpenCV. You can see the specific version for those Python libraries. You can also try the latest version. I double check that each of those versions works well with TensorFlow 2.17 and of course under the Python 3.12. And after you finish, you have to run code space and a dot, and this will launch this VS Code environment. Of course, you can use your own IDE. And after that, don't forget to change your current running environment. In VS Code, you should click Ctrl Shift and P, and now we have to choose select interpreter, and this is the list of all the installed environment in my local machine. I will choose this one, the one that we just created, TensorFlow 217. 0.17. So now we are ready to continue with to start coding. Next, before we start building and creating our model, I left a link here to the Kaggle dataset. So this is the link. Let's jump to the website. So here is the 100 sport image classification, and if we go down here, you can see that there is a train folder with all the categories, all the 100 categories. For example, if we choose air hockey, we can see all the images that are related to air hockey. Okay, air hockey is a sport. And let's see, for example, archery, and these are images from archery. And basically you can see that the images are divided to 3 folders: train, test, and validation, a very common practice. And I already download, you have to click this button of download. I already download the images, and we can see it here. This is on my local folder, it's on my local folder. Of course, you can store it in your desired folder in your local machine. So now we are ready to start coding. First of all, we will try to browse some of the images using some Python coding, and then we will generate the model. So now let's start the coding, and basically it will be an image classification pipeline using EfficientNet. So let's create our first Python code. It will be named step number 1, build the model. First, we import all the required libraries for data handling, image processing, and model building. Please notice I also paste the link for the dataset, and it will be also part of the link for the full post. So let's load all the relevant layers from TensorFlow and Keras, like dense, input, flatten, dropout. I believe we will use most of them. Let's also import some callbacks, like model checkpoints and early stopping. So we will no need to train all the epochs, so we will stop training according the accuracy or the lost value. Moreover, we will do 2 types of testing our model. One, we will do an evaluation for all the 500 test images, and the second, we will do an inference for a specific image, a random image that I will grab from the test folder. We will display it and run an inference through this image. So I believe that the last one will be importing the classification report, also confusion matrix. I don't know yet if we will do a confusion matrix. Let's start with classification report. So next we will define the path to our training, validation, and test folder. So this is the full path to the images, the train, validation, and test. Now let's define a function that the purpose is to display a random images with labels from the training dataset. So let's name it show random images with label, and we will send a path and the number of required images to be displayed. The default will be 5 images. And now we get all subfolder, all the subfolders which correspond to the class labels. And then let's shuffle the list of the subfolders to ensure randomness. So here is the random command, the shuffling command. And next we will create a figure with multiply columns to show sample images. The default will be displaying 5 images in this figure. And then now we will run a loop, and after that we will collect all image paths from the random subfolder. Once again, let's shuffle them, shuffle the images, and we will grab and select one image. Next, we will open the image using Pillow and display it with its class name. So basically, this is the target of this function, displaying those 5 random images. Great. So the title will contain the name of the image path, and along with the name of the subfolder, which is the label. Let's also choose a font, and I believe we're done. And now we just have to call the function. Now let's run the code. Before I can see, I forgot to close it here. Great, now it's ready. Let's run the code and see the result. We're expecting to choose 5 random images. Here are the images. As you can see, this is a pole vault, and this is the name of the file. This is a chuck wagon racing, javelin, hang gliding, sidecar racing. Great, it's working. Let's try another one. Let's move it to here. Great. So now, as you can see, we can we double check the images. We can load them. We can see that all the images are in the same size. I didn't change the size, this is the original size. So now let's move further and prepare the data for the training and also create our model. Okay, now we will, in order to make our model more robust, let's apply data augmentation using the ImageDataGenerator. So we will create an image generator for data augmentation and rescaling. As you can see, we will add a zoom range of 20%, also some width shift range and height shift range. So we will add more images with these minor changes. And after that, we will load our train dataset, and as you can see, during the data load we also add a categorical mode and convert all the images to 224 by 224. We will contain it on 32 images per batch, and also shuffle the train images. As for validation, we don't need augmentation, so the image generator doesn't get any parameters. And we doing the same loading process. Instead of shuffling, it will be false. We don't need to shuffle the validation images. And as for the testing, it will be the same generator as validation with no augmentation, and loading with the same parameters. Now we will build our model using EfficientNetB0. It will be our base for the transfer lane. So let's build the model based on the EfficientNet. As you can see, we are loading the object, and also loading layers and the basic empty model structure object. So the base model will basically based on the ImageNet, the 1000 images pre-trained model. We are excluding the top layers since we are going to add our layers, and we freeze all the convolutional based layers, so we will train only our custom top layer. We will use the existing weights. We add custom layers for our specific classification problems, and we use the global pull-in and dropout as well. And the last layer will be our dense 100 categories, so this is basically our target. Now we combine the base and the top layers into a final model. We compile the model using the Adam optimizer with slightly higher learning rate, and after that we will define where we are going to store our best model. Best model means that after each epoch, if there is an improvement, it will store and save the weights of our training model. So let's define a path. Let's name it best model path, and we will store it in this location, and we will name it 100 sports model.keras. So now it's the training part. We train the model using the training and the validation generator with callbacks for early stopping and checkpointing. So the early stopping will monitor the validation loss, and if after 5 epochs there will be no improvement, it will stop learning. Let's also add a model checkpoint. That means that we are going to save the model in the path, in best model path, if there was any improvement. And at last, let's plot the training and the validation accuracy, and also the loss over the epochs. So we will extract the information from the history variable, and we will grab the train accuracy, the validation accuracy, the train loss, the validation loss, and also the total number of training epochs. So basically the total, it's the actual number of epochs, and we will display it. And basically that's it. Now let's watch the whole code before we run it. Let's see if we have some syntax error. First of all, let's add some printing, and for example, let's add here the training images. So basically it's the load the train data. Okay, let's add it so we can see the progress here. The dataset, this is okay. This is the training, and another one before the validation. This is for the validation. We have to put here dot output. This is important. So this will extract the last layer, and then we are adding our custom layers like the global average, pull-in, dropout, and the dense for the 100 classes. So let's try to run it. Let's see if we have any errors. First of all, we have those 5 images. We can skip it, and now we can see here it loaded the here. This is the train images. We have, wow, more than 13,000 images, and this is the validations, 500 images, and this is the test, 500 images. So let's go down to the last line of the log, and let's wait for the starting of the training. And here it starts. We can see this is our first epoch. We can see the progress, and we can see the accuracy live and the loss live. In this part I move to a fast forward, so you can see the progress of the training. You can see that each time the training was improved, you will see a line named saving model 2, and it's our best path model. And if there was no improvement, you will not see this line. You can follow the accuracy that goes up and the loss that goes down, and if there will be no improvement for 5 epochs, the model will stop training, and we don't have to wait until 50 epochs. So the training has finished. First of all, we can see that we ran 17 epochs out of 15 epochs, and the accuracy is 0.97, the loss is 0.09, but more important, the validation accuracy is very high, it's close to 1, and also the validation loss is a very low value. And let's also look at this diagram. We can see that the training accuracy, the blue line, and the validation accuracy are say one next to each other with no spikes. It seems a very good training. Also the loss, you can see that the 2 lines are aligned together. So I believe that the training was very good, and let's continue to the next step, which is running some tests and inference over our saved model. So after the training, we would like to test our model. So we will do 2 methods. So the first one will be, we will name it step number 2, evaluate the model on test dataset. The second will be on a specific image. But let's go back for the first testing method. Now when we trained and saved our model, we would like to evaluate its performance. So first of all, let's load the trained model from the save.keras file, and let's print the summary, just a simple sanity check. And after that, let's define the test directory to evaluate the model on unseen data. And let's load and prepare the test dataset using ImageDataGenerator. No augmentation is needed for testing. We can copy, it's the same command as our previous step number 1 Python code. And now we will evaluate the model on the test dataset and print the accuracy and the loss. Next, we will import sklearn metrics to get a detailed classification report, and let's extract the true class labels, and after that predict class probabilities and convert them to class indices using argmax. And finally, we will print a detailed classification report including precision, recall, and F1 score for classes. So this will give us the ability to understand the performance of our model to the 100 classes. So let's run the code. First of all, I see here it should be evaluation. I have to drop one E. And now let's run the code. First of all, we are loading the model and print its summary. This is only a sanity check. You can see here that it was loaded successfully. And now we are waiting for the classification report and also the evaluation of all the test data. It runs now. So look here, we have accuracy of 98% for the test data, so it's a great result. Let's wait for the classification report. So the evaluation is okay. Now, as you can see here, for each of the classes we have a precision and recall. And the classification report shows most classes at 1 precision and recall. So basically it's a very good result. Here, for example, we have 0.83, where we are seeing about 0.8 recall. That's typically one class miss out of 5. So basically it's a very good result as well. Let's look more at the other result. Here it's a lower value. And look at the trapeze. The trapeze, the recall is lower. I believe that we basically maybe need more data and retrain it. But out of 100 classes, it's a very good result. And I believe we can move forward to the last step, which is running an inference with a test image. Next, let's test our model with one single image from our test dataset. Let's create a new Python file and step number 3, predict on one image. And we will import all the relevant libraries from Keras and OpenCV. And first of all, let's set an image size constant and load the trained model once again, the one that we saved in the training process. So this is where we stored our the weight of our best model. Now we are loading it. And next, let's load the test directory and list all class names to map predictions to labels. Let's print the results just for double check. Now let's run it. So we are loading the model, and let's also print the classes and the number of classes. We will need it for the prediction. So here are all the 100 classes names, and this is the total number. We have 100 classes. Now let's define a helper function to prepare any image for the model prediction. We are sending the path to the image. We are using the load underscore image from Keras to load the image and resize it to our requirement. More preparation is converting to array, and also we will normalize the image, so the values will be between 0 and 1. After that, we'll provide the path to the one sample image from the test dataset. We will try it on a bike polo image. This will be our test image. It's part of the test folders. Now let's read the image using OpenCV for display and process it for the model input. Next, we will use the model to predict the image class probabilities. Here it now. And after that, we will convert the probabilities to the class index with the highest score using the argmax function. Now let's retrieve the corresponding class label from our list of class names using the answer. Let's print the result. So this will be our class number, so it will be a value between 0 and 99. Let's also print the class name. So we will store it on the predicted class variable. Now let's use the put text and put the class name on our original image. The position will be 10 by 10 on the image. Just choose a font, choose a color, and also the thickness of the text. And at last I'm showing in order to display the image. So let's run it. So we will load the model, load our test image, the bike polo, and we're expecting to see the prediction text bike polo. So here is the image, but it's not bike polo. It says here ultimate. I think I know what is the problem, and the efficient model would like that the inference image would be with the original pixels and not be normalized between 0 and 1. It does the normalization during the inference process. So I put a comment here. Now I disabled here, of course, and now I run it again. And now it says bike polo. Let's say the text is not in the right position, so let's put it on 10 by maybe 13, and let's also reduce the size 0.7. Let's run it again, and here it is, bike polo. So we are getting the right prediction. Great, so thank you very much. I hope you enjoyed this tutorial. See you in my next tutorial, and don't forget to subscribe. Bye bye.